Hi guys, I'm back. All right, so let's talk about this one. This is the electrophysiology. This one is an extension from the, sorry, let me share screen, right? I don't think so. Share screen, okay, that's this one here, share. So this one is extension from physiology, from the cellular physiology. Cell has cell membrane. Membrane all has this sodium potassium pump. So that sodium potassium pump, do you guys remember how that works? It's right here. So if you don't remember, it's right here. So sodium potassium, ATPase, it pump 3 sodium out, pump 2 potassium in. So that causes two things. One, because it pumps less positive charge ion into the cell right here. Okay, so it will be more negative because more positive pumping out, less positive pumping in. So it's more negative. So inside of a cell will become. Let's use a different color here. How would that work? Become more negative. So cell membrane inside is more negative, outside is more positive. And the second thing it causes is that inside of cell will have a lot of potassium. Outside of the cell will have more sodium. So if we look at the intracellular versus extracellular ion concentration comparison, we will see that in the cell, not everything is less except potassium. Potassium is more in the cell compared to outside of cell. So this pump is the original source of this membrane potential because now we have negative charge to inside, more negative compared to outside. And this happens to all cells. All cells has this membrane potential. So if we put the electron, one in the cell, one out of cell as a reference, we will see the membrane potential to be negative. It's around this number, negative. So here is an example in the neuronal cell, but this applies to all cells. All cells has membrane potential. This is also called resting membrane potential. That's because the neuronal cell has non-resting, the active potential. But for other cells, majority of the cell, only they are not excitable, but they do have the membrane potential. All of them has negative minus 70 millivolt, something like that, inside of cell. So that's caused by this pump. If we only have this pump, then in the cell, we will have accumulation of potassium. It's like you keep pouring water or potassium in it. In the end, it's gonna overflow, but it's not, right? It's stable. It's because that we have a little hole here. So this one, even though we pour it in, it will leak out a little bit. So it will remain to be almost like the same. I don't want to do it. Okay. The same. Yes, see, yes. Almost like the same here around this level. So it's not overflow because this reached to a balance. This pump it in, there's a leakage here. So this one in the cell, it also has a pore here. Let potassium out. So these two cause a stable amount of potassium inside of cells. So we talked about this one already, that sodium potassium pump sodium out. pump potassium in, and there is leakage, sodium diffusion out. So it will maintain very much. You pour in potassium in, and there's a little bit leakage. And so that will make the inside of cell has a certain level of potassium, and the pump keep pumping, but there's leakage, so it's not overflow. Two factors cause negative membrane potential: sodium potassium ATPase, and leakage of the potassium more than sodium, but essentially that's potassium effects. So leak channel, we have a leak channel in the permeability. So this one is how leakage it is. Sodium has the highest. Sorry, potassium is the highest. Potassium is highest. So so we dump a lot of potassium in the cell, but a little bit leak it out. So then we have this difference in the cell. Here we have potassium in the cell. Outside the cell, we have sodium. Also, we have negative charge ion in the cell, positive charge membrane potential. So we now have two kind of like gradient. One is the electrical gradient, that positive charge will tend to go in because inside is more negative. If it's positive charge, it will tend to go in because inside is more negative. If it's potassium, potassium will try to go out, even though potassium positive, but potassium will try to go out because inside has too much potassium. Sodium will try to go in. It's not just sodium more outside than inside, so by diffusion, it will diffuse in. It's also inside is more negative, so that will also drive the sodium into the cell. So as long as there any chance, if there is a door for any ion, they will move depending on their charge and also their concentration. So that leads to the excitable cells, the action potential. So what cells have membrane potential? All cells have membrane potential, but not all cells have the action potential. Not all cells are excitable. Only these three cells are excitable: neurons, muscle, secretory cells. So these three are excitable. It means that here we have membrane, okay, Here we have cell membrane is negative. For other cells, the majority of cells, this membrane remain to be -70, something like that, throughout the whole life. Red blood cells, white blood cells, skin cells. So they have membrane potential, and it's very stable. But for the other cells, they can be excited. It means that their membrane potential will become not just remain as -70. If they got excited, if they got triggered, they will generate action potential. That's how our sensory works. Like you can smell. It's because that fragment going to your nose acts on your chemoreceptor in your olfactory bulb, And then it will, so here is your nerve. Nerve has a little hand out there, and cell body, sorry. All right, so cell body. And then send to your brain. Your brain right here. Your brain. So it will send to, sorry, send to, I don't mean to do that. Oh, all right, send to your brain. Okay, so here you have fragments that the smell, you know, flow, acts on it, start to act on it. When it acts on it, how would your brain know that it smell good or smell bad, right? Your brain must receive some signal from your nose, right? And you know, the reason is that here the memory potential was negative. It's so sensitive. Was negative. Maybe if I make it smaller, would that help? Yeah, oh no. Oh. Okay, inside of cell is negative. Okay, and then it generates an action potential. And that action potential will then travel. So if let's say action potential is a blue one. So that action potential will then travel all the way, let's see, to the blue. Yes. So this one here, so that action potential will then travel all the way to the brain. All the way to the brain. So it will, action potential is something, you know, beginning in the resting, it was negative memory potential. And this one will make it become almost like zero or a little bit positive. Here it's zero. And that memory change. So here it's a membrane. It was negative and it turned to almost like positive. So that will propagate to the brain. And then your brain will know. So that's very important for our, you know, function that we can communicate with outside world. We can receive sensory. Sensory is the way that we really, you know, participate live, feel the life. So that's action potential. All right, so here, all cells, not all cells, only neuronal cell, muscle cell, secretory cell have the memory potential. That is that memory during the resting state is a negative charged membrane potential, and it got excited when there's stimulus. It will become positive. It was in this stage. This one is because it's negative. Negative is polarized compared to outside, compared to the zero, right? So it's polarized. So this one is polarized. All cell memory is polarized. And this process, this phase is called depolarization because it's polarized become not so polarized. So this phase is called depolarization. And then it reached the peak, and then it will then quickly turning back. This one is repolarization, because it regained that polarization. And then it reached the resting memory potential again. So this is the action potential. This action potential is the same in neuronal cell, in muscle cell, in secretory cell. It's all the same. So we learn this one, we know all other membrane potential, all other cells action potential. So this action potential has some phases. We need some terminology we need to know. First, this one is the resting state, resting membrane potential, and the stimulus need to make it above a threshold. So here is a threshold, RESHOLD, threshold. Only when that stimulus is strong enough to make it above the threshold, then the membrane will trigger an action potential. This action potential has two phases. One is depolarization phase. Then we have repolarization phase. During the depolarization phase, of course, the cause of the depolarization is there is a sodium channel open. Sodium channel open. There is a sodium channel open. So say there was no sodium channel, but now we have a sodium channel. Sodium channel open. So sodium channel open. Now if the sodium channel open allows sodium to move, will sodium outside has more sodium, inside has more potassium? If the sodium channel open, will sodium move in or move out? Outside has more sodium, so sodium will move in because of the concentration gradient. Because of the concentration gradient, sodium will move in. And that move in because this is positive charge ion. So it will make it become more positive, and that's the cause of this depolarization, to make it more positive. And then it will close it, opens up another channel, which is a potassium channel. Now, when we have this potassium channel, will potassium move out or move in? Inside potassium, outside sodium. Will potassium move in or move out? It will move out, right? Because it's more potassium in the cell. So potassium will move out. And that move out of potassium, because potassium is a positive ion, it will make the inside to become more negative, because that's positive. So we have the repolarization when the potassium channel open. Now it will return back to negative because a lot of positive charge ion move out, become more negative. But then potassium will close. This channel will close. This close is not that fast. So there is a time that we may have potassium move out too much. So we have a hyperpolarization. Hyperpolarization, because this one is polarization, but now it's overpolarization, over too much, hyperpolarization. Then it returns to the resting membrane potential. So a couple of things: phases, depolarization, repolarization. Which channel is open? Sodium channel is for depolarization. Potassium channel is for repolarization. All right, so you need to know that. Those are quiz questions, you know. Sorry about that. So again, terminology. action potential has this resting membrane potential, then threshold. Only the stimulus is strong enough to be above the threshold, it will trigger. Say if the stimulus is so small, it's like a whispering. It's just too small, you cannot hear anything. And only if the stimulus is strong enough, it will trigger action potential. When action potential is triggered, it will have depolarization followed by repolarization. Depolarization is a sodium channel. This channel is called a voltage-gated sodium channel. It's because that this channel open due to the stimulus, and the stimulus basically change the membrane potential to be above the threshold, So that's sensitive to the voltage. Only if it's high, a little bit enough, then the threshold, then it opens. Sodium flow in, cause increase the membrane potential to generate this depolarization. And then it closes, followed by repolarization. It's a voltage-gated, again, potassium channel. So this potassium channel open because the membrane is neutral. It was around this like a voltage. So they never seen this before. This is 0. It used to be always like negative 70. So now it's 0. Potassium feel like, okay, it's my turn to open. So it's sensitive to voltage. Their opening is gated by the voltage. Now potassium channel open, potassium flow in to make it, potassium flow out because inside has more potassium. So potassium flow out to make the inside become more negative. And that brings the membrane potential back to polarized, back to about -70. Then we have a period of hyperpolarization. And then back to the resting membrane potential. So threshold is that if we have stimulus, say this one is not reached to the threshold yet. So this one is stimulus. If we have stimulus this level, it will only cause the membrane potential to be high a little bit. This membrane potential is not an action potential. This membrane potential has a term called stage. Don't worry about the term. Let me check on that. But it's not high enough to trigger an action potential. And if your stimulus is this high, it's not high enough. Only if your stimulus is this high, then you trigger an action potential. If your stimulus is this high, right? Would you have a higher membrane potential, or would you have exactly the same membrane potential? If you have higher stimulus, you will have the same membrane potential. You will have the same action potential. You will have the same action potential. So action potential is either yes or no. It's not like a lot more or a lot less. It's only yes or no. You either trigger it or not. If you trigger it, it will be the exact same thing. So this one is called all or none principle. You either all or 0. Once we have this action potential, it will induce their neighboring membrane, because now you for example, it was like everybody is all negative. Now we have some region turn to positive, and that positive will become like, the spot that can contagious the neighboring membrane, because this one is positive, this one negative, then they will disturb the local area, and so everyone else will become positive. So by having one action potential in a local spot right here, action potential, that will make the neighboring one to become positive, to become positive, to become positive, to become positive. So that will make the membrane potential that will make the action potential to propagate from one original spot to the remote area. And so when in the beginning, this one is, okay, so you receive signal, like you hear one saying words, like the other person saying something, or you smell, or you feel, you touch things, right? You touch, and then you will feel something that will tell your brain, this one is smooth, this one is cold, and then that will trigger an action potential. That action potential will then travel along the membrane toward your brain. So the quiz question would be that, where is action potential travel on? Where is that travel? Action potential is membrane potential. So it travels along the membrane, cell membrane. So cell membrane is like that. Membrane potential is like that. For the neuronal cell, it's just the cell become different shape. This is differentiated cell. So it already find its calling, its destination. It become very, very like dedicated to its calling to become neuronal cell. And so its membrane, its cell become elongated. And again, this is membrane potential. I hate it. I hate that. So inside is negative, okay? And the action potential will make it positive, and that will travel along the membrane. All right, so when you have one stimulus, you can stimulate it again, but not immediately. That's the time called refractory period. You cannot stimulate the same spot twice in a very short period of time. Our cell cannot respond to that. This is called refractory period. Refractory period has two types. One is absolute, means that if you trigger an action potential, and during this time, you want to trigger it one more time, you cannot, because now that it's already activated, you cannot add anything to it. So this one, that stimulus will not be responded. So that's called absolute. It's the time when our sodium channel is open, a lot of sodium coming in. So you cannot open it anymore. It's already opened. Now, if your period reached to here, in this period, that sodium is already closed, potassium opened, and it's not closed yet during this hyperpolarization, during this repolarization, and the hyperpolarization. You stimulate it, it will be difficult because now it's hyperpolarized. It's too negative, so you need to push it harder. In the resting, is minus, in this case, is minus 90, right? So you only need to bring it, say, to minus 70. This is threshold, for example, threshold. You only need to increase 20 to trigger an action potential. Now, in the hyperpolarized, this one may be minus 100. So you need to increase 30 millivolt. You need to push it harder. It's not impossible. It's just your stimulus need to be harder. And that is called, another type of refractory period is called relative refractory period. It's not impossible, it's just your stimulus has to be higher. All right, so that's the very basic electrophysiology. This one is universal idea throughout all these excitable cells. And this one laid the foundation for our next talk in each excitable cells. The next one will be muscle cells. That's an excitable cells. And then we will talk about the nerve cells. That's excitable cells. And all of them follow the same principle that they have resting membrane potential, they can be excited, and they can generate action potential. And this is action potential. All right? So I will see you next time then. Stop recording. Is that? Yes.